CellCal. That quiz will be up all week, and it closes next week, Monday. So some folks have already done that. 2 attempts. It's not a super hard quiz, so be sure to get that one done as well. Okay, let's get going. We're going to start by taking up the VOR ILS questions. Not VOR ILS, the transponder DME questions that we covered off last week. So let's look at that. And so, question number 1. An aircraft transponder unit transmits a coded reply to an air traffic control ground station interrogations. Question 2, the air traffic control radar beacon system utilizes 2 main types of ground-based radar. They're known as PSR, which means primary surveillance radar, and secondary surveillance radar. Which one of those 2 radar systems actually has anything to do with your airborne transponder unit?
Secondary?
Yep, secondary surveillance radar. So the secondary surveillance radar, if you don't remember, is an antenna mounted on top of the primary surveillance radar. The primary surveillance radar looks like a dish, parabolic dish, and the secondary surveillance radar is just sort of a stick type antenna, and it rotates around with the primary radar. Question 3, the air traffic control transponder unit. Your transponder unit, the one that lives in your aircraft, actually receives these interrogations on 1030 megahertz. However, it transmits its replies back on a different frequency on 1090 megahertz. So we're dealing here with UHF, line of sight, it's pulse. So the higher you are, the better off you're going to be with this system. In Canada, there's 2 main types of air traffic control radar beacon system interrogations. They're called the Mode A interrogation, and the second one is the Mode C interrogation. That being said, in the United States, question 5 is a little, maybe should be reworded. It's not recently. Recently, if you think 1992 was recent, okay, in the United States there was introduced a 3rd type of interrogation system many years ago called Mode S interrogation. So that's also in the game now here in Canada. So basically we have 3 main types of air traffic control radar beacon system interrogations: Mode S, Mode C, and Mode A. Question 6, the interrogation, actually Mode S interrogation, the S stands for select, and why that's kind of a nice system to have. The newer system is, first and foremost, it will provide air traffic control with your aircraft's registration as soon as you're within basically distance of the air traffic control site. Without an air traffic controller actually having to make radio contact with you to retrieve that information. Question 7. That new Mode S, also works in conjunction with the aircraft's TCAS system, so traffic alert and collision avoidance system, to help minimize the risk of mid-air collision. It's a mandatory requirement to have Mode S transponder when you have a TCAS system, which is not a problem because both transport category aircraft and commuter aircraft have to have both those systems anyway. So, question 8, a Mode A or Mode C interrogation consists of 3 pulses. So we're talking about pulse 1, pulse 2, and pulse 3. However, it's the spacing between the leading edge of the P1 pulse and the leading edge of the P3 pulse that will determine the mode of interrogation question being sent. Okay, remember the interrogations are coming from air traffic control. They're being sent on 1030 megahertz. So your transponder's picking them up on that frequency and examining the time lapse between the P1 and the P3 pulses to determine the question. Question 9, P2 pulse, that pulse is known as a side lobe suppression pulse, and that pulse is going to help to eliminate the proper wording is fruiting or garble on the ground station's radar scope, which we refer to as the planned position indicator. And remember, P2 is there to, it's sent in an omnidirectional fashion, always 2 microseconds after P1, and its purpose in life is to stop your transponder from replying to false side lobe interrogations. And that's usually going to happen when you're closer to the air traffic control site. Question 10, an ident button is activated by the pilot when requested by air traffic control to make a positive ID of your aircraft. Okay, so the term would be squawk ident. You'd squawk a number and then hit the ident button. Question 11, that ident has to be sustained for a minimum of 20 seconds to be considered intolerance. So the avionics guys usually set it to somewhere between 20 and 25 seconds. And that really is your 15th pulse. When you send back your information, you can send a maximum of 15 pulses. It's actually the 15th pulse called SPIP, the Special Purpose Identification Pulse. So when you hit the ident button, you're sending the 15th pulse on the pulse string on 1090 megahertz back to air traffic control. Now, on to DME, question 12. The approximate, it's not the actual, it's close. The approximate frequency range of the DME system is from 960 megahertz through to 1215. That's why when you look at the antenna system for a transponder and a DME system, it's the same antenna. It looks like the exact same antenna. It's because it is. When you buy one of those antennas, it says right on the packaging, transponder / DME antenna. Okay, so whether it's the spike, the little spike, or the small little shark fin, little blade, it can be used for either system. Okay, some students ask me, can they share the antenna? No, you have to buy one specifically for transponder use and another one, a separate one for DME, but they could be the identical antenna. They look identical. Canador, I think I mentioned in class, so as not to mix them up when people are looking at the aircraft antenna systems. Canador typically uses the little spike for the transponder system and the small blade for the DME system. Make life easier. Question 13, the aircraft DME will display slant distance. So it's not actual ground distance. What they refer to in the slides, I believe, as geodesic distance is made good over the ground. It's slant distance in nautical miles. It's from your aircraft in the air, basically diagonally to the ground station. So it'll also display ground speed in knots and time to station in minutes. So a more modern DME display unit provides 3 things. Okay, distance in nautical miles, ground speed in knots, and time to station in minutes. Question 14, the DME ground stations are often co-located with a number of really other ground stations. It's like Wendy's, Tim Hortons, and Harvey's Swiss Chalet. So you can have a DME ground station co-located with a VOR station. It's exactly what North Bay has. North Bay has a VOR DME station. You can also have a DME station co-located with an ILS station. So you have an ILS / DME station. You see more of that in the States. And it's really the TAC part of VORTAC or TACAN. TACAN is the military. The military gave us all these systems. So TACAN stands for Tactical Air Navigation. And VORTAC is basically a civilian VOR station co-located with a military TACAN station. So the TAC part of the station, which is TACAN, can provide DME information. 15. The DME system is channel paired and will automatically tune when either a VOR frequency or a localizer frequency is selected on your aircraft nav receiver. So you're never going to have to put in one of those UHF frequencies from 960 megahertz through to 1215 megahertz. It's going to happen automatically for you when you channel your VOR frequency or your localizer frequency into your nav unit. The only other system that was channel paired that I seem to remember was glide slope. Glide slope was channel paired to localizer frequencies. So whenever you put a localizer frequency in that part of the instrument landing system, the glide slope also came alive. Okay. 16, there are two types of channels when it comes to DME. You're either an X channel, which is civilian, or a Y channel, which is military. The difference being the X channels have a 12 microsecond pulse spacing between the P1 pulse and the P2 pulse, whereas the Y channels, the military channels, have a 36 microsecond basically pulse spacing between P1 and P2 pulse. And I think if you remember, there was also, to identify an X channel over a Y channel, you look at the second place of decimal on either your VOR frequency you enter in the nav receiver or your localizer frequency. If the second place of decimal is a 0, it means you're dealing with an X channel for DME. If the second place of decimal is a 5, you're dealing with a Y channel when it comes to DME. And yeah, 17, a DME station can be identified by a 3-letter Morse code identifier. It's a little bit unique in that it's not coming at you at the normal audible tone. It's not at 1020 hertz. Instead, it's at 1350 hertz. So it's slightly higher in pitch when you listen to it through the audio system. Okay. And I think I mentioned in class, North Bay VOR and North Bay DME, the Morse code identifier is the same. It's YYB. So if through your audio controller you had selected VOR audio through the nav receiver selection switch and DME audio through the DME receive selection switch, first and foremost, they would never overlap. You wouldn't hear the two of them ever overlap. And you would hear 3 VOR Morse code identifiers, YYB, on 1020 hertz. And then thereafter, you would hear the 1 DME Morse code YYB on 1350 hertz, slightly higher. So it's sort of a 3-to-1. You hear 3 VOR Morse codes, and then you hear the 1 DME. 18, so the unique pulse pair coding that everybody's DME, when you first turn it on, does, it encrypts, so it creates its own pulse pair pattern. Everybody's is different, and it changes every time you turn the unit on and off. It's kind of like fingerprints or DNA, and we refer to that unique pattern or encryption as jitter. So everybody's DME, when it's operating, is sending jitter from the sky on one frequency, and the ground station's picking it up and resending it back to you on a different frequency. In case you didn't remember, and this fill in the blank sheet doesn't say it, but ground station, if you're an X channel, if you're operating civilian X channel, the ground station replies always come back to you 63 megahertz lower than what you sent to them. And if it's military Y channels, the ground station reply always comes back 63 megahertz high. Okay, that's sort of the way it works. And there was another term, it doesn't seem to be on this fill in the blank either. It was a term called squitter. Anybody remember what squitter is? How can 86 people go silent?
Isn't it when they're randomized?
So jitter's randomized. Every aircraft sends its own unique pattern that's jittered, and it has to be because you're looking for your own replies back from the ground station. So everybody's has to be unique. But squitter doesn't come from your aircraft. So there's only two players in this game: your aircraft, which is really the interrogator, and the ground station, which is the replier. So the ground station, in order for it to work properly, okay, when I say work properly, it has to maintain a 50 microsecond delay time before it sends everybody's pulse pairs back into the sky. In order for that to happen, it has to be running at full capacity, meaning there has to be a full house using it, a full complement of aircraft using the DME station. Well, let's think about North Bay. Like, North Bay is not a busy airport, but it certainly does have DME. There's just a handful of aircraft in the vicinity of North Bay using the North Bay DME station. So it definitely doesn't have a full house. So in order for it to work properly and maintain the 50 microsecond delay time before it sends pulses back into the sky, it has to insert basically fake pulses. It has to fill its own system up. And we call those fakes, those duffs, we call that squitter. Okay, the station has to be processing 2,700 pulse pairs every second. So when it's not doing that, when it's not full, it inserts these duffs, these fakes, and that's referred to as jitter. Not jitter, sorry, squitter. So the ground stations insert squitter when they're not full. And
Hey, Darren?
Yeah.
What if the opposite happens? What if it has too many planes at once?
Yeah, that shouldn't happen. It's 2,700 pulse pairs per second, so it's a lot more than that. It's just when they're coming in, when you think about it, is one at a time, right? 2,700 pulse pairs per second coming in the door. It won't be full. It won't be
All right.
full. Yeah. So, sort of the joke when I went to school here, the teacher used to love to refer to, well, they said, well, jitter, squitter is not jitter, and jitter is not squitter. However, squitter is jittered. Kind of a little play on words. And he's right. Okay, jitter is not squitter because jitter comes from aircraft. It's the unique encoding that each aircraft DME produces. And squitter is not jitter because squitter comes from the DME ground station to fill the system when it doesn't have enough users. So yeah, you're right. Squitter is not jitter and jitter is not squitter. However, squitter, the one introduced by the ground station, is indeed jittered. It's randomized, and it has to be. Okay, you can't. Everything that's in the system has to be unique for you to be able to identify your own aircraft pulse pairs when they come back to you. That's the only way DME can work. It's the idea of radar. When you send something and get it back, you're interested in first identifying that it is indeed yours, and secondly, the time lapse that took place between when you sent them and when you get them back. But you have to be able to recognize your own jitter over all others. Okay, so when you think about this poor little box, this DME box, when it starts to formulate pulse pairs, okay, let's say at 12 microsecond spacing between P1 and P2 at a jittered rate, it has to put that in a memory location. And then it has to basically listen on whatever frequency they're coming back on. Okay, it'll be 63 megahertz low ball. And it has to look at everybody's coming in. Now, those aren't mine. That's not mine. That's not mine. That's not mine. That's not mine. Until it finally says, no, okay, that one is mine. So that pulse train is mine. And then no, that's not mine. That's not mine. That's not mine. That's not mine. Oh, those ones are mine. It has to get a lock. It has to figure out, okay, by looking at everybody's, okay, when it comes back specifically. And then it can go out of that'll be in search mode, and once it locks on, it'll go into track mode, and you'll see the display come up. Good. Okay. Any more questions on that one? Okay, that's good. No questions is always good. Okay, let's look at TCAS. So TCAS stands for, officially, Traffic Alert and Collision Avoidance System. Don't you think they should put an A between the abbreviation, the T and the C in TCAS? TCAS. Kind of just sort of, if you look at the abbreviation, Traffic Collision Avoidance System. No, it's Traffic Alert and Collision Avoidance System. It's proper name. Question 2, TCAS is a secondary radar system that operates like an airborne air traffic control station. So having a TCAS on your aircraft is like having your own little airborne air traffic control station built right into your aircraft. Question 3, TCAS is indeed independent but compatible with the existing air traffic control facility. 4, and we got to check a box here, the